Welcome back to The Explainer, where we love to get our hands dirty with tricky problems and break them down. Today, we've got a really cool one for you, pulled straight from a multivariable calculus exam. So let's kick things off with a little puzzle, one that's actually at the core of multivariable calculus and even 3D graphics. Picture this. You're standing on the side of a cone. Which way is straight out? How would you point perfectly perpendicular to that curve? That's exactly what we're going to figure out. And here it is, the exact problem we're going to solve together. This isn't some made-up example. It's from a real university exam. We've got the equation for a cone and a very specific point on it, 3, 4, 5. Our job? Find the vector that's normal, perpendicular to the cone, right at that spot. All right, before we jump into the numbers, we need to make sure our toolbox is ready. We're going to need 3 key concepts to solve this thing. First up, what is a normal vector? The slide gives a great analogy, a flagpole on a curved hill. It's not leaning forward or backward, it's sticking straight up, totally perpendicular to the ground right where it's planted. That's our goal. Find the vector that points perfectly straight out from the surface at our point. Okay, so here's our game plan. It's a simple 3-step process. First, we'll find 2 vectors that lie flat on the surface, our tangent vectors. Then, we'll use a neat trick to find the one vector that's perpendicular to both of them. And finally, we'll plug in our specific point, 3, 4, 5, to get our final answer. Easy enough, right? All right, pencils ready? Let's get into the calculation. It's time to put our plan into action. Okay, step 1. Find those tangent vectors. We start with this equation for the cone. You can think of it like a recipe for creating the cone. You give it an r, how far from the center, and a theta, the angle, and bam, it gives you the x, y, and z coordinates for a point on the surface. So to get our first tangent vector, we take the partial derivative with respect to r. Now, what does that really mean? Well, just imagine you're at the very tip of the cone, and you walk in a straight line up the side. The direction you're walking in, that's what this vector, r sub r, represents. For our second tangent vector, we do the same thing, but this time with respect to theta. So instead of walking up the cone, imagine walking in a circle around the cone, staying at the exact same height. That path gives us our second direction, r sub theta. Now we have 2 different directions along the surface at any given point. Step 2, the cross product. This is where the magic happens. We have 2 vectors that are lying flat on the surface. How do we find the one direction that's perpendicular to both of them at the same time? Well, that's exactly what the cross product is designed to do. It's a mathematical tool that spits out a vector perpendicular to the 2 you started with. It's perfect for finding our normal vector. And this is how we set it up. We use this table, which is called a determinant, to organize the whole calculation. You just pop the components of our 2 tangent vectors in there, and you're ready to go. After you crunch the numbers in that determinant, this is what you get. And what's so cool about this is that it's a general formula for the normal vector. It works for any point on the entire cone. All you need are the r and theta for that point, and you've got your normal vector. Okay, on to step 3. We have this awesome general formula, but we need the answer for one specific point, 3, 4, 5. So we need to figure out what r and theta correspond to that point. If we look back at the original equation, it's pretty clear. X is r cos theta, y is r sine theta, and z is just r. So we can just substitute directly. We know x, which is r cos theta, is 3. We know y, which is r sine theta, is 4. And we know z, which is r, is 5. So we plug those into our normal vector formula, and what do we get? We get -3, -4, 5. Boom. That's our answer. Okay, so we've done the math. We've got our vector, -3, -4, 5. But remember, this was a multiple choice question. So the big reveal is, does our answer actually match one of the options? Okay, here they are, the 4 possible answers from the exam. Have a look. Wait a second. Our vector, -3, -4, +5, it's not on the list. Did we do something wrong? Nope. Don't panic. There's just one last little piece to the puzzle. So our result isn't there. But think about it. The normal vector is the one that's perpendicular. It can point out from the surface, or it can point in. Both directions are perfectly perpendicular, right? So a vector pointing in the exact opposite direction is also a totally valid normal vector. And how do we find the opposite? We just multiply by -1. And bingo. When we flip the signs on our vector, we get 3, 4, -5. And that is exactly option C. We nailed it. Our calculation was spot on. Great. So we solved a tricky exam question, but so what? Why does any of this actually matter outside of a math class? Does this concept of a normal vector ever show up in the real world? Oh, you have no idea. This math is literally the foundation of pretty much all modern 3D graphics. In video games, in animated movies, in architectural software, you name it. The computer needs to know which way every single tiny polygon on a surface is facing. And how does it know? The normal vector. It's the key to making anything on a screen look solid and real. Seriously, think about it. Every time you see a realistic shadow fall across a character's face, or a glint of light reflect off a car in a game, that's a direct result of this math. Without the normal vector, the computer has no idea how light should bounce off that surface. Everything would look totally flat and wrong. It's the secret sauce behind all that visual magic. And the speed this happens at is just mind-blowing. Your graphics card isn't just doing this calculation once. To render a complex 3D scene in real time, it's calculating thousands, maybe millions of these normal vectors for every single frame 60 times a second. It's an incredible amount of math happening constantly. It really makes you wonder, right? What other invisible mathematical engines are chugging away behind the scenes, shaping the digital world we interact with every single day? So next time you're lost in a stunning video game world, just remember the elegant, powerful little bit of calculus, the normal vector, that's making it all possible.